Hi, my name is Jennifer Miller, and this is my Lab 5 Breaking with Faraday presentation for Physics 2212. We will start with the introduction. So in this lab, we use a magnet and a rolled tube of aluminum foil to produce an induced current when we drop the magnet through the roll. We will complete this experiment 5 times and record the average time it took for the magnet to fall through the tube by viewing the experiment recorded on our smartphones. Using the values in this lab, we can create a computational model of the lab in order to compare the results between the experimental and computational models. On this slide, we will discuss the physics concepts and observations that are displayed in this lab. There are many physics concepts used. Newton's second and third laws are both applicable to this lab, as well as the Biot-Savart law to calculate the magnetic field, Faraday's law to calculate current, and superposition to add up the values of each ring. One observation I found is that your mu value that was calculated in Lab 3 can skew your results if it's too high. Here is the data from my experiment. To complete this experiment, you need to know the magnet mass, length of aluminum tube, width of the foil, both the inner and outer radius of the foil, the mu value calculated in Lab 3, and the average drop time from your experiment. The chart to the right displays the time in seconds that I determined from each of the magnet dropping trials. Now we will discuss the computational aspect of this lab. In this presentation, I only included the sections of code that I thought were most important to this model. You can see the remainder of my code by using the link to my GlowScript code. The first section of code is the function created to determine the magnetic field of the bar magnet. We created this section of code in Lab 3, so that part was relatively simple. The second section of code shown represents the formula needed to calculate magnetic flux. We needed to calculate d flux dt for each ring as the magnet falls through it. To continue, this final section of code shows how to compute the magnetic field at each ring, and from there, we know the total magnetic force is the magnetic force plus the force of gravity. To finish the code, we write 2 lines that update the position and velocity of the bar magnet as it drops through the tube. Here is the output of my code. As you can see, the velocity versus time graph at one point turns into a constant value for most of the graph. Additionally, the time in the tube as computationally calculated is 4.51 seconds, which is much longer than the experimental time calculated. Now we will interpret the simulation. In the simulation, the red color represents clockwise flow and the blue represents the counterclockwise flow. If the magnet were to be flipped, it would still continue to fall in the same negative y direction. However, flux would decrease in the opposite direction that it is now. Additionally, I believe the real-world system to be more accurate because if you do the experiment as explained in the instructions, there is little room for error. Additionally, I believe there to be such a large difference between my computational time value of 4.51 seconds and the experimental value of 1.2 seconds because the mu value could have been incorrectly calculated in Lab 3. On the velocity versus time graph, we can see that the forces acting on the bar magnet will sum to 0 because they are equal and opposite in magnitude. Finally, if the resistivity of the conductor were reduced, the current would increase, causing the magnet to take a longer amount of time to fall. Additionally, if there were holes cut into the tube, the magnetic force and induced current would both decrease, causing the magnet to drop much faster.